Okay, Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera. Okay, starting from this week until week 8 or 9, we will cover chapter 3, which is the Simplex algorithm. So, in the previous chapter, we have learned the graphical method for solving two variable LP problems. Unfortunately, most real-life LPs have more than two variables, which encourage the development of an effective method called as the Simplex algorithm, which is introduced by George Danzig in 1947. We devote most of this chapter to a discussion of this algorithm, which is used to solve even very large LPs in many industrial applications. This chapter explains the main features of the Simplex algorithm and the procedure for solving any LP model in details. Then, the Big M method and also two-phase method are introduced to solve complex LP problems. And the last section in this chapter will discuss the relationships between the primal and dual problems, and then followed by the important concept of duality. This concept reveals that every LP problem has associated with it another LP problem called the dual. The relationships between the dual problem and the primal problem prove to be extremely useful in a variety of ways. Nowadays, Simplex algorithm is a standard tool that has saved many thousands or millions of dollars for many companies or businesses, and its use in other sectors of society has been spreading rapidly. A major proportion of all scientific computation on computers is devoted to the use of linear programming. Okay, basically there are 4 steps in Simplex algorithm. The first one is LP form. So far, you have learned about this LP form in the previous chapter. So for LP form, left hand side is either greater or equals to right hand side, or less than or equals to right hand side, or equals to right hand side. And for right hand side, it must be positive constant value. Okay, so we have learned this in chapter 2, right? Okay, second step, what we need to do is we need to convert this LP form to standard form. Okay, so for standard form, left hand side must be equals to right hand side. So any constraint with less than or equals to the left hand side must be added with slack variables. Constraint with greater or equals to the left hand side, we need to minus with surplus variables. Surplus, also known as excess. So many books use this symbol SI. Sometimes there are books use E for excess. Okay, And then third step is we need to convert this standard form to Tableau form. So for Tableau form, you need to make sure two things. The first one is the right hand side must be non-negative constant value, non-negative constant, and then second one is there is a BV, there is a BV or basic variable, BV for each constraint. And then in the final step, you can use Simplex algorithm. Execute Simplex algorithm. Okay, so how to convert an LP to standard form? LP can have both equality and inequality constraints. Before the Simplex algorithm can be used, LP must be converted into an equivalent problem in which all constraints are equations and all variables are non-negative. So left hand side must equals to right hand side. A linear program in which all the variables are non-negative and all the constraints are equalities is said to be in standard form. Okay, standard form is attained by adding slack variables to less than or equal to constraints and by subtracting surplus variables from greater than or equal to constraints. So for this case, for example, this one is greater or equals to, so the left hand side is greater than right hand side, right? Therefore, we need to minus with the excess or surplus. So left hand side, whatever we have on the left hand side, we need to minus with surplus or excess. Okay, and for less than or equals to, the left hand side is less than right hand side. Therefore, in order to make it as an equation, we need to plus left hand side plus with slack variable. Okay, slack and surplus variables represent the difference between the left and right sides of the constraints. Slack and surplus variables have objective function coefficient equal to 0. Okay, let's look at example 3.1. Convert the following LP to standard form. Maximize z equals to 4x1 plus 3x2 subject to x1 plus x2 less than or equals to 40. Second constraint, 2x1 plus x2 less than or equals to 60. x1 and x2 must be greater or equals to 0. So the solution is we need to change these regular constraints to equations. Okay, so left hand side must be equals to right hand side, because for these two constraints, the left hand side is less than or equals to right hand side. Therefore, we need to add slack variables to these constraints. So x1 plus x2 plus s1. 1 here because this is the first constraint. Then for the second constraint, 2x1 plus x2, because it's also less than or equals to, therefore we need 2 plus s2. Okay, so instead of 2 variables, now we have 4 variables, x1, x2, s1 and s2 must be greater or equals to 0. And for the objective function, the coefficient for slack variables are zeros. So 0 s1 plus 0 s2. Okay, so in summary, if a constraint I of an LP is a less than or equals to constraint, convert it to an equality constraint by adding a slack variable as I. Okay, let's look at the next example, example 3.2. Change the following LP to standard form. Okay, so for this example, all constraints are greater or equals to sign. Therefore, we need to minus the left hand side with whatever excess or surplus or excess that we have on the left hand side, so that all these constraints equals to right hand side. Okay, so the first constraint 400 x1 plus 200 x2 plus 150 x3 plus 500 x4 minus s1, because this is the first constraint, equals to right hand side 500. Second constraint 3x1 plus 2x2 also greater or equals to, so we minus with s2 equals to right hand side, which is 6. Third constraint 2x1 plus 2x2 plus 4x3 plus 4x4 equals greater or equals to, so minus whatever surplus or excess that we have, so s3 equals third constraint equals to 10. And then the fourth constraint 2x1 plus 4x2 plus x3 plus 5x4 also greater or equals to, so we minus surplus variable s4 equals to right hand side, which is 8. So now we have x1, x2, x3, x4 and also these 4 surplus variables. So don't forget to put it here as I greater or equals to 0 and I equals to 1, 2, 3, 4. So for the objective function, actually we have surplus variables in here, but the coefficient are all zeros. So 0 s1 plus 0 s2 plus 0 s3 plus 0 s4. Okay. Okay, so in summary, if the ith constraint of an LP is a greater or equals to constraint, it can be converted to an equality constraint by subtracting the surplus, or also known as excess variable, Si from the ith constraint and adding the sign restriction as I greater or equals to 0. Okay, so after we convert an LP form to a standard form, then we need to convert to a Tableau form before we can execute Simplex algorithm. So how to convert a standard form to a Tableau form? A set of equation is in Tableau form if for each equation or constraint, its right hand side is non-negative, and second one is there is a BV or basic variable for each constraint. So how to generate an initial Tableau form? An artificial variable must be added to each constraint that does not have a basic variable. So usually happens when constraints with greater or equals to signs. Okay, let's look at example 3.3. Refer to example 3.1. Find the Tableau form of the LP. So we have obtained a standard form for this LP in example 3.1. So for example 3.3, we need to convert this standard form to a Tableau form. Convert to Tableau form. So how do we do this? Okay, so the first one is you need to make sure the right hand side of the constraints are all non-negative. So first, let's check. First constraint, positive 40, so that's fine, check. And then second constraint, also positive, so check. And you also need to make sure that there is a BV for each constraint. Okay, so for these two constraints, actually we can write as matrix A. So for matrix A, the first column x1, x2, s1, and s2. So we have 1, 1, 1, 1, 0, 1, 1, 0. Second constraint 2, 1, 0, 1, 2, 1, 0, 1. So for this example, actually BV for the first row, for the first constraint, or for the first equation is from here, because it's actually identity matrix 1001. So S1 is the BV for the first constraint, and then for the second constraint, S2 is the basic variable. Okay, so actually this standard form is also Tableau form for this LP model. Okay, for the Simplex algorithm, so we have done step 1 and also step 2. First one is convert the LP to standard form. And then step 2, put in Tableau form to obtain a basic feasible solution where there is a BV for each equation and the right hand side are non-negative. Okay, to understand the rest of the steps, let's look at example 3.5. Okay, so you are given this LP form, and then we need to solve the LP using the Simplex method. So first step is convert to standard form. Okay, because all of the constraints are less than or equals to sign, Therefore, we need to add the left hand side with slack variables. So plus S1, then plus S2, plus S3, and then plus S4. S1, S2, S3, and S4 greater or equals to 0. And then for the objective function, plus 0 S1 plus 0 S2 plus 0 S3 plus 0 S4. Okay, next we need to check whether this standard form is already a Tableau form. So for the first constraint, first one is we need to make sure the right hand side is on greater or equals to 0, right? Right hand side must be greater or equals to 0. So 48, 28, and 5. Okay, so check. Okay, another thing is there is a BV for each row, for each equation. So how do we know this? We need to put this constraint into a matrix A. So 8, 6, 1, 1, 0, 0, 0. Okay, 4, 2, 3 over 2, then we have 0, 1, 0, 0, 2, 3 over 2, 1 over 2, 0, 0, 1, 0, and then 0, 1, 0, 0, 0, 0, 1. As you can see here, x1, x2, x3, and then we have s1, s2, s3, s4. As you can see, from s1 to s4, these 4 columns, it forms an identity matrix. So for the first constraint, s1 is the PV. Because here the coefficient is 1 and the rest of the row zeros. Okay. Second constraint, S2 can become the BV. Third constraint, S3, and fourth constraint, S4 can become the BV. So there is a BV for each row. So now we want to obtain an initial tableau. First step, you need to move all the right hand side of the objective function to the left hand side. Okay, so now sec minus 60 x1 plus 30, minus 30 x2 minus 20 x3, and 0 s1, 0 s2, 0 s3, 0 s4. Okay, so for the initial tableau, for the first row, we call this as row Z or row 0. So for the first column, column Z, the coefficient is 1, right? So 1 here. And then for the second column, column x1, the coefficient is negative 60. Okay, this one is equals to 0, right? Because nothing left on the right hand side. Okay, and then negative 30, negative 20 for x3, and then 0, 0, 0, 0. Then right hand side is 0 because everything is already moved to left hand side. Okay, for row 1, we look at the constraint. The coefficient is 8 for column x1. Here 0 because there's no z in this constraint. 8, 6, 1, and then 1, 0, 0 equals to right hand side 48. Okay, we can actually take from this matrix A. 8, 6, 1, 1, 0, 0, 0. Okay. Next, 0, 4, 2, 3 over 2, and then 0, 1, 0, 0, 20. Third constraint, 0, 2, 3 over 2, and then we have 1 over 2. It's better to write as a fraction. 1 over 2, 0, 0, 1, 0, 8. And the fourth constraint, fourth row, we have 0, 0, 1, 0, 0, then 1, right hand side equals to 5. Okay. So for this initial tableau, BV is on this column. So we have S1, S2, S3, and S4 as BVs. And the rest of the variables are considered as NBV on non-basic variable. So we have x1, x2, x3. Okay, so we have 7 here, 4 BV and 3 NBV. So in step 3 of the Simplex algorithm, we need to check the optimality condition. So in here, we need to find an entering variable to be a BV for the next tableau, which is tableau 1. Okay, how to do this is for this example, the objective is maximize, right? So here maximize. So for maximization problem, we choose a BV with the most negative coefficient as an entering variable. So for this case, x1 will be the entering variable. Okay, because negative 60 is the most negative coefficient on this row 0. Okay, next we need to choose for feasibility condition in step 4, we need to choose a living variable. Okay, for living variable, we need to eliminate one of these PV. So we need to check the ratio by using a ratio test. So right hand side over coefficient on this pivot column. So we call this as pivot column. Okay. So 48 over 8, we have 6. For the second row, 20 over 4 equals to 5, and then 8 over 2. 8 over 2 equals to 4, and then 5 over 0. So for this case, there's no value, so just put dash. Okay, so by using this ratio test, in order to choose a living variable, we need to choose the one with the lowest ratio. So here 4 is the minimum ratio. So we will eliminate S3 from this row, SBB, then we change with X1. Okay, so pivot row. Okay, the intersection between pivot row and pivot column is known as pivot value. So for the next tableau 1, we need to change this value to 1. Okay, so here's Z, S1, we have S2, but now for S3, we have replaced this with X1 and then S4. Okay, so in order this value to be 1, so we need to divide all this row with 2. So row 3 new, row 3 over 2. Okay. So 0 over 2, 0, 2 over 2, 1, 3 over 2 over 2, we have 3 over 4, right? 3 over 4, 1 over 2 over 2, so we have 1 over 4 for this column, and then 0 over 2, 0, 0 over 2, 0, 1 over 2, 1 over 2, okay, 0, and the right hand side becomes 4. Okay, so for the next row, okay, so row 0, we use this formula, row 0, here X1 has now become a BB, therefore the value here is 1, and the rest of the rows must be equals to 0. Okay, so in order to make this value negative 60 to be 0, then we need to use this formula. So R0 new, we refer back to R0, and also the first row that we return here, which is the pivot row from this initial tableau, so we always refer to R3. Okay, new, R3 new is 1, so we always refer to this one. So because it's negative 60 here, therefore here we put plus 60, and then we use this formula for this row 0. So R0 new equals to row 0 plus negative 60 R3 new. So R3 new is 1, right? So negative 60 plus 60 times 1. So we get 0 for this column. Okay, therefore, by using this formula here, so for row 0 or row Z, we will get 1, 0, 15, negative 5, 0, 0, 30, 0 and 240. Okay, so for row 1, the formula is row 1 new, row 1 and row 3 new. Remember that we always need to refer to this row, pivot row. Okay, so because this one is 8 for row 1, therefore here is negative 8. So we get 0, 0, 0, negative 1, 1, 0, negative 4, 0, 16. Okay, for row 2, the formula is row 2 new, refer to row 2 and row 3 new. So again here the coefficient is positive 4, therefore here negative 4 times row 3 new. So we get 0, 0, negative 1, 1 over 2, 0, 1, negative 2, 0 and 4. For the last row, row 4, new equals to row 4 because it's already 0 here. So just copy 0, 0, 1, 0, 0, 0, 0, 1, 5. Again, we repeat step 3, which is optimality condition. So we need to check whether this Tableau 1 is already optimal or not, because it's maximization problem. We need to choose the most negative coefficient, so x3 as the entering variable. So it means that this Tableau is not optimal yet because it still has a negative coefficient at row 0. Okay, so x3 will become an entering variable. So by using ratio test, we need to identify the leaving variable. Okay, so ratio test 16 over negative 1. So we don't take negative coefficient in pivot column, so just put dash, and then 4 over half, you get 8, right? 8, and then 4 over 1 over 4. So 4 over 1 over 4, you get 16, and then 5 over 0. So we also don't take 0 for ratio test. No negative and no 0, okay? If you find the ratio negative or over 0, then you just put dash. So for this case, the lowest ratio is 8. Therefore, S2 will become the leaving variable. Leaving variable. Okay, so for Tableau 1, the pivot value is 1 over 2. So for Tableau 2, BV will be S1. So here X2 will become a new BB, sorry, X3, and then X1, S4. So NBV other than these 4, X2, S2, and S3. Okay. So here Z, S1, now X3, X1, and S4. So again, we use ERO because X3 now is a PV, therefore here it should be 1. And the rest of the rows 0, 0. So for row 2, new equals to row 2 over half. Therefore, over half, therefore row 2 times 2 to row 2. Okay. So we multiply this row with 2. So 0, 0, negative 2, 1, 0, 2, negative 4, 0, and 8. Okay. For row 0, always refer to this row, go to new. So because in here it's negative 5, therefore positive 5. So for row 0, by using this formula, we get 1, 0, 5, 0, 0, 10, 10, 0, 280. For row 1, refer to row 1 and also refer to row 2 new, because in here it's negative 1, therefore here the coefficient positive 1. So row 1 new equals to row 1 plus row 2 new. Okay, so we obtain a new row for row 1 as 0, 0, negative 2, 0, 1, 2, negative 8, 0, and 24. For row 3, new, row 3, and refer to row 2 new, because it's 1 over 4 here, so negative 1 over 4. So for row 3, we get 0, 1, 5 over 4, 0, 0, negative 1 over 2, 3 over 2, 0, and 2. And the last one, row 4 new, because here is already 0, so we just copy the old row 4. So S4, 0, 0, 1, 0, 0, 0, 0, 1, 5. So repeat step 3 again. We check the optimality condition by checking the coefficient in row 0. So because this one is maximization problem, we check at row 0, there is no negative coefficient, right? Therefore, this Tableau 2 is the optimal Tableau. All variables have non-negative coefficient in row 0? Yes, right. All BV have 0 coefficient in row 0? Yes. Any NBV has 0 coefficient in row 0? No. Therefore, this LP has a unique optimal solution. So, the optimal solution is S1 equals to 24, and then we have X3 equals to 8, X1 equals to 2, S4 equals to 5, and all NBV equals to 0. So here X2, S2, S3 equals to 0 because NBV, the value is always 0. And then from this Tableau also we get Z value is 280. Z equals to 280. Or you can also substitute these values, the BV values into the objective function to calculate the Z value. Okay, as a conclusion, the Simplex algorithm have 5 steps. So in step 1, we need to convert the LP form to standard form. Okay, and the second step, you need to put the standard form into a Tableau form to obtain a basic feasible solution, BFS, where there is a BV for each equation and the right hand side are non-negative. Okay, in step 3, we need to check the optimality condition by looking at row 0, determine whether the current BFS is optimal by checking the coefficient in row 0, the coefficient less than or equals to 0 for minimization problem, or coefficients greater or equals to 0 for maximization problems. If yes, then stop. It is already optimal. If not, select an entering variable, which is the variable with the most positive coefficient from row 0 for minimization problem, or the most negative coefficient for row 0 from row 0 for maximization problems. Okay. Next, in step 4, we need to check the feasibility condition. So here, we select a leaving variable by using a ratio test, where the leaving variable is the BV associated with the smallest non-negative ratio with strictly positive denominator. So after we have selected a leaving variable in step 4, then in step 5, we need to do ERO. So for pivot row, we need to replace the leaving variable in the basic column with the entering variable. And then for new pivot row, we need to calculate a new pivot row equals to current pivot row over pivot element, the pivot value. So all other rows, including row 0 or row Z, the formula is new row equals to current row minus its pivot column coefficient multiplied by new pivot row. And then we go back to step 3 to check whether the new Tableau is already optimal or not.
Please do all of these questions as your homework and submit at Google Classroom by this Friday. If you have any problem, feel free to discuss in WhatsApp group. Thank you.